Okay, good. Let me jump ahead.
Okay, so you probably did look at the, if you looked at the PDF of this, you thought, man, this is short, which it is, but it's also the one of the foundations of the content or the material that you've got to understand, got to get it. So that's why I said I think it was last year, or year before, I said, I'm going to split this up because I felt like it was just a rush through it. And I would rather take our time and make sure everybody understands it rather than, trying to just push through. And we got plenty of time in the semester with the way I have the material set up. So receptor exposure. We're going to look at this as the outline to sort of keep us on track of what we want to talk about this morning. So by definition, receptor exposure is talking about the amount of ionizing radiation that actually reaches the receptor and is used to produce or create the viewable image. So it's how much is left over radiation once it passes through the patient and makes it to the IR. So it's a dose to the IR. Okay, so how much actually is going to make it through and interact with the IR? That's what we are talking about when we talk about receptor exposure. So, the controlling factor for receptor exposure is going to be mass. Other factors do influence receptor exposure for sure. But the one that we want to use to control receptor exposure is going to be mass. And we'll talk about the why of that in just a minute. This picture here is from your Auber book. And it just shows you that if you have on the left, if you have less mass that's being applied to the patient, then it just makes sense that you're going to have less that actually has an opportunity to make it through to the IR. If you have more mass, then you're going to have more exit radiation reaching the IR. So we have the primary beam, which is what? What is the primary beam? Primary radiation beam. It's the photons that are what?
Going to the patient?
Yes, that are being directed at the patient. That's the primary beam. The exit beam or exit radiation, again, is what's left over after it's passed through the patient and is actually interacting with the IR. So it just makes sense that if we start with more mass, then more mass has a chance of actually getting to the IR. So signal versus image noise. So signal is what we consider to be the good part of the beam. Okay, that the signal is the image forming photons that actually make it to the IR and help create the image. And image noise is the not so good stuff. Okay, so there's different types of noise that we can talk about. What we're talking about here is actually can be referred to as, in parentheses, you can put beside of image noise, you can put photon starvation. That's a newer term that the ARRT has introduced. So photon starvation, which means exactly what it says. The IR has been starved of photons. There weren't enough photons that made it to the IR to actually create a diagnostic image. So it's noisy. So there's a couple of examples that you can think about when you're thinking about signal and noise. Now, I know that y'all are very young class, okay? So back in my day when we listened to the radio, okay, anybody still listen to the radio? And when you're traveling along and you can hear everything really well, but the further you get from the tower for that station, what happens? Static. you begin to get this static noise, right? And so the amount of signal is decreasing and the amount of noise is increasing, and that's bad if you're trying to hear the song, right? So it's the same thing with signal and noise in the creation of an X-ray image. We want lots of signal. We want good image forming photons. We don't want there to not be enough so that we have this photon starvation. We can also get noise. There's things that we'll talk about next semester, electronic noise. There's scatter. Okay, so we talked about scatter a little bit last week. So scatter, we have the primary beam, right, that interacts with the patient. And the photons can either travel all the way through with no interaction at all and hit the IR, right? That's one thing. So that's called transmission. And then we have photoelectric absorption, where the photons absorbed in the patient's body, especially in things like bone, right? And we also said there was a third thing that could happen, and that is that the photon interacts, loses part of its energy, and goes off in a different direction. And that's scatter. That also creates noise on our image. Okay, but what the type of noise that we're talking about here is photon starvation, or lack of enough photons to create the image. So God bless you. So you can also think of it this way. During a light rain, you can see raindrops on like a dry sidewalk. So let's say it's just starting to barely rain. And you can see that they're not evenly distributed, right? You might have a drop here and there, and it's very random, right? But during the heavy rain, which they're calling for tomorrow in the morning, the same uneven distribution is there. You just can't tell it anymore, right? Because they're still just dropping wherever, but there's so many of them, you don't see that random pattern anymore. So the X-ray beam, you can think of as the shower of X-rays, which have a random distribution, just like the rain shower. So random distribution to the IR, just like a rain shower. But when low mass values are used, you have fewer photons striking the receptor. Then you can see this in the image as a grainy or freckled appearance. That's called quantum model. So quantum means number, right? When we talk about quantum, we're talking about number. So we call it grainy. That's sort of an old film term that we had, because there was actually crystals or grains in the emulsion of the film. And so when we talk about an image looking grainy or freckled, I also like to call it sort of that salt and pepper look. And we're going to see that in lab this week. So all of those things cause a problem in being able to, for the radiologist to be able to dictate that image or read that image as diagnostic. So when we don't use enough mass, we have too few photons that are there, we're going to see that randomness in the pattern of the image, which if we have more photons creating that image, just like with the rain shower, then we won't see that. And so that's what we want. We do not want to send an image to a radiologist that is noisy. Okay, that's going to create a problem with that image being diagnostic. So the best way to subdue this is to increase the information carrying exposure or signal. So again, we either got to get closer to the tower for the radio station, right? To get rid of that noise that would be drowning out the music or whatever it is that we're trying to hear. The other thing you can think of is this way. Think of if we're all in here, okay, and let's say Sam is talking. She's trying to ask a question, and everybody else in here starts talking. To be able to hear her well, she's either got to start talking a lot louder, or everybody else has got to be quiet, right? So we got to increase the signal and decrease the noise to be able to hear what she's trying to say. So signal good, noise bad, right? So we always want the signal to noise ratio to be high. We want lots of signal and as little noise as we can possibly get. On track here. So we've already talked about the primary exposure factors that we know, which are what? You need to know this for the test. What? Say it loud. MA, time, SID, KVP. Okay. So now we're going to begin to break those down into individual characteristics about them. So learning as much as we can about each one of those now that we've sort of broadly talked about them and what they do. So milliamperes, or MA, is talking about the current in the tube. The time, again, is the duration of the exposure. How long is the exposure going to be? A combination of that in MA and time equals MAS. Remember that the unit of time in that formula is what? Seconds. That's what the S stands for. So the MA times the time in seconds equals your MAS. And in general, when you're setting manual techniques, which is what we talk about when we're not using the AEC, okay, so when you get to clinic, they're going to use the AEC a lot, which is great. That's what it's there for. But when you're here, we're teaching you to set manual techniques, because if you go somewhere to work that doesn't use the AEC as much, then you need to know how to do that. So most of the time when you're in clinic, if you're not using AEC, you're going to be setting mass, okay, a combined MA and time. Just like in our labs with this Siemens equipment, we don't have the option to break it out and set a separate MA and time. We can set an overall mass, and then we can adjust the time, remember, in milliseconds, but we can't set the MA. So that's done in the background. And we'll look at the breakdown of that here in just a minute. So we talked about source to image distance, the distance from the focal spot to the image receptor. And that's why when you pull your tape measure down, it doesn't start at 1. It starts at like 11, because it's taking into account the distance from where the focal spot actually is on the anode to where that tape measure starts. It's taking that distance into consideration. And then the KVP, kilovoltage peak, is the speed of the electrons and affects the energy of the photons produced. And we're going to talk about that one more in a few weeks. So milliamperage is the measure of the quantity of the current that's passing through the tube at the time of the exposure. So what is the current that's being applied to the tube is determined by the MA that is set. Well, again, we aren't physically setting the MA ourselves, but the machine is doing that in the background. And when we get to lab, I'll try to show you how you can see what MA was actually used, and we can look in the DICOM header. It is set on the control panel of some equipment. Ours is not. It does determine how hot the filament gets. So what is the filament?
Or the electrons are produced.
Yeah, so the filament is the coil that is in which side of the tube?
Cathode.
The cathode. Yes, so this is all a really good review for the test as well. So the filament is housed in the cathode, but specifically, yes, in the focusing cup. Yes. So there is a direct relationship between the MA and the quantity of X-rays that's produced. So if direct, meaning if one goes up, the other goes up. So if MA goes up, then the quantity of X-rays produced goes up. It's actually directly proportional. Okay, so if MA is doubled, then that means the amount of X-rays produced would be doubled. That's the direct, means they both go up. Proportional is if one, they change in the same amount. So if one is doubled, the other is doubled. So if it is directly proportional to the amount of X-rays that's produced, that means it's also directly proportional to receptor exposure. Remember, again, we talked about a few slides earlier, if there's more mass being directed at the patient, so to speak, then there's going to be more receptor exposure, right? So the thing with MA is that it doesn't affect subject contrast, spatial resolution, or distortion. Now, I realize that we have not really discussed those terms yet. That's coming. All this is coming in the as we go through the semester. But just remember that there are 4 big topics, 4 characteristics of the X-ray beam that we're going to talk about this semester. And the first one we're talking about today, receptor exposure. So receptor exposure is one quality or characteristic. The other 3 are subject contrast, spatial resolution, and distortion. So just know that MA only affects receptor exposure. It doesn't change the quality of the beam. It doesn't change anything about the spatial resolution. It doesn't change anything about distortion. All right, let's move on to exposure time. So it is what controls the length of the X-ray exposure by determining how long the current will be passing through the tube. So how long is that current going to be applied to the tube? It also controls the quantity. It is also a directly proportional relationship to receptor exposure. So if time is increased, receptor exposure will increase. If time is doubled, receptor exposure will double. Okay? And also, time does not affect the other 3 big qualities of X-rays that we talk about. It doesn't affect subject contrast. It doesn't affect spatial resolution, bless you. And it doesn't affect distortion. So are you seeing a pattern here? With MA and time so far, the relationship to the amount of photons created and therefore to receptor exposure is what? The same, right? Exactly the same. Now, specifically some more about time, and we're going to do some practice problems in lab this week, because this basic formula of MA times time equals MAS, you have got to know from here to eternity. You can never forget it as long as you stay in X-ray. It's a fundamental formula that you've got to know. So some things about time stations. Well, some of this older equipment that you probably will not see may still have their time stations in fractions. And everybody goes, oh, right? We don't love fractions. We don't like fractions. But the older equipment, I can think of an older, we don't go there anymore. We don't send you there anymore. But one of the older places in Greenville had some equipment that actually still, it had fractions and you pushed a button. And so most of them are going to be in milliseconds these days. The equipment that we have in the lab, we're setting milliseconds unless we purposely want to set a long exposure time, and we'll talk about when we would want to do that in a minute. So a millisecond, which is generally what we're setting on our equipment, you have to remember is 1,000 times smaller than a second. So you're going to have to remember how to convert. And again, we're going to get practice with this in lab this week. So converting times from milliseconds to seconds and from seconds back to milliseconds, because you have to have your times in seconds to use the formula, but you have to have it in milliseconds to be able to set it on the control panel. So we'll go back and forth. Again, to convert to a fraction, you just put the number of milliseconds over 1,000. To change to a decimal, put a decimal point to the right of the number, then move it 3 places to the left. That's when you're converting milliseconds to seconds. For example, 15 milliseconds would be how many seconds? And the better way to write that would be to put a 0 in front of the decimal place. I should have done that. That's the more proper way. So 15 milliseconds would be 0.015 seconds. So again, if you have some time in between Yolanda's and lab, or in between mine and Yolanda's, you can go ahead and look, well, section 1 especially, you can go ahead and look at your lab manuals. There's just some practice problems in there that we're going to look at, so you could sort of get a jump start on that if you want to. And actually there's a nice little review of converting times. So when we put those two things together and we get milliampere seconds or mass, again, not to be confused with MASS, two totally separate things, then your mass is going to represent the total quantity of X-rays produced in an X-ray beam, because it's going to take into account both the quantity of X-rays and the length of time that they're produced. So it's a combination of the two, okay? But everything else about it is exactly the same as it is individually for MA, individually for time. The relationships are the same to the number of photons that are created and therefore the amount of receptor exposure. So again, it also does not affect contrast, spatial resolution, or distortion. So do you understand now why we want to use mass to control receptor exposure? Why is that? Because what? It doesn't affect the other three big quality factors that we talk about. It only affects receptor exposure. So that's why we want to use mass to control our receptor exposure. There are other things. We're going to learn that KVP affects it. We're going to learn that SID affects it. We're going to learn that whether or not you use a grid affects it. There's a whole lot of other things that affect receptor exposure, but mass is the only one that doesn't affect anything else. So therefore, that's the easiest way to control receptor exposure, is to adjust the mass. So one example that I like to give of this to help you understand it is to think about your paycheck, okay? So your MA would be like your hourly rate, okay? So let's say you make $25 an hour, okay? That would be like your MA station, okay? Your exposure time would be how many hours did you work? So to get an idea of what your overall paycheck is going to be, what do you have to do? Yeah, you have to put them together, right? You have to multiply what your hourly rate is by how long you work to get your total paycheck. That's the same thing with the MAS formula. MA times time equals MAS. We have to know what current is being applied. We have to know how long is it being applied to know the total number of photons it's going to be produced, which therefore will affect receptor exposure. Does that make sense? Okay. So it's just a simple algebraic equation. If you know two of the three, you can figure out what the third is. So in the equation, MA times time equals MAS. It can also be written these other two ways, right? Is everybody going back to math 109? 109 or 110, having nightmares about going back to math? Well, that's a part of what we have to be able to do. So it's just a simple formula where if we know the MA and the time, we can figure out the mass. If we know the MA and the mass, we can figure out the time. So we can rewrite that formula in three ways. So one year I had a student say, "Why are you taking us back to third grade math?" And I said, because a lot of people don't remember third grade math. Math is one of those things, when you don't use it, you lose it, right? So we're going to start at the beginning. That way everybody gets a review and can understand what it is that we're doing. So we never want to just assume that people remember things from years ago, right? So reciprocity law, that is the name for this formula. So MA times time in seconds equals MAS is how you write reciprocity law. So what it's stating is that there's a variety of different MA and time settings that could produce the same mass and therefore the same receptor exposure. So The only exception of this is at very low or very high time settings, it may vary a bit. So when we get in those extreme, like super, super low exposure times or really, really, really long exposure times, we may get a little fluctuation there. But in general, there's multiple combinations of MA and time that can equal the same mass. So there's a number of ways that you could get paid $100, right? So somebody tell me one combination that would give you $100 if your rate of pay was what?
$25 an hour and you worked 4 hours.
Yes. If your rate of pay was $25 an hour and you worked 4 hours, what would be even better?
$100 an hour.
Yeah. If your rate of pay was $100 an hour, you only had to work 1 hour, right? So there's multiple combinations of, pay and time work that can give you the same paycheck. Same thing with mass. There's multiple combinations of MA and time that can give you the same mass. And we're going to talk about, well, how do we know which combination is best? So there's basically 3 reasons that we might want to change a combination. And that's to control motion, if we want to use a small focal spot, if your equipment is set up that way, and to use what we call a breathing technique. So let's look at those 3 things. So I know that you have not had this yet, but does anybody have any idea what that's supposed to be an image of?
Spine.
The spine, the lateral spine, so lateral lumbar, lower back area. To control motion is probably the primary reason that we would use a particular combination of MA and time to control motion. So because motion is the greatest detriment to good spatial resolution, do you see how blurry that is, that image? If that's your back, do you want that image to be the one that the radiologist gets? Absolutely not. You can't tell if there's a fracture there. It could be very subtle and it would be missed. It's even really sort of hard to tell alignment on that with that much motion. So to avoid motion, the best thing that we can do is use the shortest exposure time possible, because that gives the patient what? Less opportunity to move. So if we can use the shortest exposure time possible, that's going to give us the least chance for motion. So if we're talking about combination, and I was going to write on the board, but I realized they're not leaving expo markers in here. I guess they don't, I don't know. Anyway, so I have to remember to bring one up next week. But you can see that 10 mass can be produced using at least those 4 different combinations there. So 1/10. So I mainly put these on here to help show you relate fractions to decimals to milliseconds. So you can sort of see that. So if we had 100 MA, 1/10 of a second would be 0.1 seconds or 100 milliseconds. That's all talking about the same thing, right? So we could have that combination to give us 10 mass. We could have 200 times 1/20th of a second or 50 milliseconds. 400. So what is happening to the time station as we increase the MA there? Is it going up or down?
Yeah.
It's going down, right? So as our MA goes up, our time is going down to maintain the same mass value. So again, the higher our rate of pay, the less we have to work to get the same amount of money, right? So always think, if you start to get confused, take it back to something that every day, like a paycheck, as we all know, we're gonna know what our paycheck is. I'm gonna know what my paycheck's supposed to be, so I can tell if it's right. So that is the primary reason that we would make an adjustment to our MA time combination, is we're trying to get the shortest exposure time we can possibly get, so that hopefully our patient doesn't have time to move. Okay, this will be especially important for what type of patient? babies, children, and also the other end of that, very elderly people that maybe have dementia or something, they can't follow instructions, or maybe they have some kind of something that makes them shake or things like that. So we want to try to keep those exposure times really, really low in those situations. One of the other times that you might adjust your MA time combination, and with our equipment, because we don't have the ability to physically set an MA station, this really doesn't apply. But with our old equipment, the focal spot was connected to the MA station that you set. So once you went over 160 MA, like when you were setting your MA station, if you went over 160, it automatically put you on large focal spot. Okay. So with our equipment, we really don't have that. But if you have equipment where it lets you select your MA station independent of anything else, then sometimes you would have to use a lower MA to be able to be on a small focal spot. Okay, so the focal spot size is physically smaller and can tolerate more or less heat than a larger focal spot. The smaller can tolerate what? Less. So we don't want a really high current trying to be applied to a small focal spot. We would want a lower MA to where that focal spot can tolerate the heat that's going to come off of the filament. So when concerns about motion are not a factor and you need to have a lower MA station, because we're going to learn that focal spot also affects your spatial resolution. So I think I gave this example of like a paintbrush. So always think back. If you're going to try to paint really carefully around the edge of this board, do I want a really gigantic brush or do I want a small brush to get those fine details? I want a small brush, right? Because I'm trying to get really good detail down through there. If I'm just trying to put some paint on the wall, am I going to use the same size brush that I trim out with? No, I'm going to either use a big brush or a roller, right? Because I'm not as concerned about fine details there, right? So the small focal spot you're going to use when you're looking for really fine details, when you want really, really good spatial resolution on things like extremities. You know, your distal extremities, fingers, hands, wrists, toes, feet, ankles. And that last statement just is talking about that your focal spot may be determined by the MA stations. Like that's how our old equipment was. It was inherent in whichever MA station you chose.
I have a question.
Yes.
So the spatial resolution is based on the focal spot, so it's not the MA that's adjusting the spatial resolution.
That's right.
Okay.
What's the confusion is that with higher MA stations, you can't use a small focal spot. So the MA is not what's affecting the spatial resolution. The size of the focal spot is what's affecting the spatial resolution. Does that make sense? So with our equipment, you don't really have to worry about it because you can just select large or small. It's not, you don't know what MA station's being used because that's all happening in the background. So this really isn't an issue for you with this equipment that we have, but some equipment out there, because when you go to clinic, there's 20 different clinic sites and all of the equipment may be different. And so some equipment, it may choose the focal spot when you choose your MA station, or it may be independent and let you choose your small or large independent of an MA station. So the part of it that is affecting spatial resolution or detail is the size of the focal spot, not the MA. Does that answer your question? Still confused? Okay. Hopefully after lab, it'll make more sense because we're going to actually go through and do some activities. Good question though. All right. And so the third time that we may adjust our MA time combinations would be if we actually want to use what's called a breathing technique. And so this is a purposeful, long exposure time. The patient, you have the patient just breathe, you tell them just to breathe normally, and it uses motion to our advantage. And so there are 3 specific cases of when you would want to use a breathing technique. And these are about the only 3 that I ever used the breathing technique for. I can't really think of any others. The oblique sternum, which is this little picture right here, right there, and you can barely make out that's the manubrium of the sternum, and here's the body. These are where the ribs connect. The lateral thoracic spine, which is right here, and then the transthoracic lateral humerus. And so what is in common? What do all 3 of those things have in common about where they are located? In the what? Yeah, the chest area, right? And so we know that we have lungs there, we have ribs. And so it can be very difficult to see these, especially like the sternum in the RAO, it can be difficult to see that because you're having to deal with, you think about where the sternum lies. Here's the sternum, and then you got part of the heart, and then you got the spine, and you got the ribs. And so there's a lot of things that can obscure being able to see that. And so what happens is if you set a breathing technique, then you're purposely going to use a very, very low MA and a very, very long time, right? So that your exposure is 2 to 3 seconds long. Okay. And what we're doing there is we're actually using motion for our benefit. And so what happens when you do that is it blurs the lung markings in the ribs for better visualization of the structures you're trying to see, like the sternum, like the thoracic bodies, vertebral bodies, like the humeral head and upper, third of the humerus. So very, very low, and again, this is if your equipment allows you to do that. So the way we would do that with our Siemens room is we would have a mass value in mind, whatever our mass value would be for these parts, okay? And so we would set our mass, and then for the time, the exposure time that's right below it, right? What would we do to that exposure time? Run it way up, right? We could run it as high as it'll go. I think the service guy and I looked a couple of weeks ago, and I want to say that maybe two seconds or 3, it may have even been 3 seconds that we were able to get it up to. And so in the background, if we run that time all the way up to say we're able to get 3 seconds, I can't really remember. Say we're able to get 3 seconds. What would our MA station be? Like in general?
Really low.
Really low. Really low. We don't have the ability to set it, but in the background, if we give it a particular mass and we give it a time, then it's going to adjust that MA station to be really, really low in the background. A lot of the newer digital equipment, 1 second is as high as you can get. So it's a little more difficult to get a good breathing. A good breathing technique, your exposure needs to be at least 2-3 seconds if possible, just to give time. And you tell the patient to breathe normal, and then they start breathing weird. Like you say, just breathe normal, because they start thinking about it, right? So a lot of times I would just really not say to the patient, but it just depended on the patient. Sometimes I wouldn't even tell them, and I'd just walk out and I would just start making the exposure and not tell them, because when you tell them, then they start thinking about it, right? So when somebody says, don't act weird, what do? You start acting weird. So anyway, there'll be times that you'll use this, and Yolanda will talk about this. She'll refer to it as orthostatic breathing. So when you get to certain things in her class, she will mentioned orthostatic breathing. That's what she's talking about, is breathing technique, where you use super low MAs and really long times. Okay, your exposure indicator. That is any numerical value displayed on the image that represents the level of receptor exposure received. It's not a measurement of patient dose, it's a measurement of receptor dose. Now, our exposure indicator, so exposure indicator is this big umbrella, right, that covers a lot of very specific manufacturer specific terms. Ours is EXI. That's what our equipment has. You may see some that are just EI, which is exposure index. Ours is an exposure index, but they add the X in there, so EXI. You may see an S value. You may see an LGM value. That's a little bit older. Most of those have gone away. You may see, let's see, what does what the Phillips is. EXIS or something like that. So it's an exposure index sensitivity number. So there, and we'll talk more about this next semester. All these manufacturers have their own. And there's been a push by the National Physicists Board. Hey, manufacturers, please, can we all agree on one thing and have it be the same across the board? We're still 15 years later working on that. So it is just some way for you to know whether or not the factors that you used were appropriate for that patient. So ours is an EXI. We've talked a little bit about this already, that the range is 100 to 500. Remember how when y'all been looking at each other's images that you're evaluating and you're looking at that range, it has a directly proportional or linear relationship to receptor exposure, meaning if receptor exposure doubles, then the EXI should double. So if you use twice the mass that you needed for that projection, whatever it is, then you're going to see your EXI value double. And we're going to actually do some experiments with that. I think we do that this week. So in summary, MA times time equals MAS. That is reciprocity law, can be written as that formula. It controls the intensity of the exposure at the receptor and has a great deal to do with image noise, quantum model, or photon starvation. All those terms are talking about the same thing. Quantum model, photon starvation. All right. Any questions so far? The activities that we do this week in lab are related to this material.
This is chapter 6, right?
Well, I don't know.
Oh, no, I was like following.
I give you page numbers. I don't give you chapter numbers.
That's chapter 6. Yeah. Okay. What was in the schedule?
Because this material is scattered throughout the book.
I was like trying to follow this. I was like,
Yeah. So part of it's here, and then part of it's in another chapter. Yes.
Is this on test 1 or test 2?
This will be next week. Now, the basics that we've already discussed with, it being a primary exposure factor, that kind of stuff will be on the test, on this test that we're taking this week. But this real specific stuff, that will be the next. So there's, so speaking of anything else related to this stuff for today, before we move on and do a little 20-minute review here. Good. Hopefully after lab, that's the plan, is that we introduce it in here and then we do these activities and then hopefully it all comes together and makes sense. Okay, so let me sharing that. I'm going to actually stop the recording.